Hi, I want to show you why you should be pumped about pumps. My name is Hillary Johnson. I'm currently a PhD student at MIT in mechanical engineering. I design adaptive hydraulic mechanisms to improve centrifugal pump efficiency. Energy efficiency opportunities in pumping systems shows potential for terawatt savings of energy globally. Pumps are essential to our industrial and municipal systems, including clean water distribution, wastewater treatment, pumped hydro storage, crop irrigation, building HVAC systems, petroleum and mining, to name a few. Pumps in all these industries are major energy consumers. And in fact, pumps consume 6% of US electricity and a larger percentage in emerging economies. That's equal to 225 terawatt hours of electricity per year, equivalent to the annual generation of 56 Hoover dams. This produces 112 million metric tons of CO2, equivalent to 24 million cars. In these systems, energy saved is energy gained. And in order to improve the efficiency of pump systems, clear strategies and stakeholder action needs to be identified and incentivized. In 2016, Schenker published a comprehensive review of energy efficiency opportunities in pumping systems. He gives a thorough review of the state of the art for component selection, system dimensioning, and controls, as well as explores the trade-offs of technology within each of these categories. I highly recommend the read. I find it useful to think about this in a different framework, based on stakeholders, thinking about design, selection, and operation. Pump design determines the baseline hydraulic, volumetric, and mechanical efficiencies. Selecting the right pump for a system determines the matching of the system operation and duty cycle with the pump efficiency. And the operation uses available controls like variable speed drives to adjust the pump to meet changing system requirements. From a stakeholder perspective, design engineers determine the equipment efficiency, contract engineers select and design the systems for implementation in specific applications, and plant managers are boots on the ground deciding how to operate the system. Each stakeholder needs to take action to improve the overall system efficiency. Schenker's comprehensive review captures many important best practices, but from a design perspective, the design engineer and company leadership need to prioritize efficient designs and practices, with incentives from customer demand as well as legislation. Furthermore, companies as well as academia needs to invest in research and development to design reliable pumps with broader efficiency curves, as well as develop new means of pump control beyond variable speed drives. For selection and system identification, better system characterization and metrics to compare component and system efficiencies will prioritize efficiency in the selection process. And during operation, it's important to enable plant managers to continuously measure and control system efficiency. I think of pump efficiency as an energy source, and by improving the efficiency of significant industrial and municipal systems, we reduce the energy we need to produce. In order to improve pump system efficiency, we need to scale industrially proven, currently existing technologies, as well as invest in researching new technologies to apply a terawatt scale. The priorities I recommend for accelerated deployment are continuous data collection on pump operation, implementing efficiency metrics, as well as installing efficient pump and motor hardware. These may seem basic, but they form the fundamental building blocks that then lead to the development of new technology like system controls and optimization. Using deployed hardware and systems, we need to develop these system controls for reliable and scaled implementation. In order to give you context for these strategies, I'll give you a brief primer on the classical models for pump operation and then compare them to real data from a New England wastewater treatment plant. So, a pump is designed to hydraulically and mechanically meet functional requirements based on the application. The performance of a pump is traditionally visualized by a pump characteristic, and this characteristic shows the operating continuum of the pump. Generally, as flow increases, the pressure decreases. This characteristic can be measured experimentally for particular pumps, and an efficiency curve shows the efficiency of a pump for a range of flows. Efficiency is the energy out over energy in, and we often capture the wire-to-water efficiency of a pump and motor together. The best efficiency point is the pressure and flow point at which the pump operates most efficiently. Now, pumps don't operate in isolation, they're connected to systems. And as these systems are traditionally represented by a system characteristic, showing the demand for pressure across a range of flows. The pump and system characteristics can be plotted together. And in this model, the point where the system characteristic and the pump characteristic intersect is the operating point of the pump. Some systems are constant, but often they're shifting over time as demand for flow and pressure changes. The operating point shifts as the system shifts, moving along the pump characteristic. Now, remember the best efficiency point. Ideally, the pump would be selected such that the operating point is at the best efficiency point of the pump. However, as operation changes, there are sacrifices in efficiency when the pump operates away from the BEP. In order to address this, there are ways to control the operation of the pump to match the operating point. One way is to use a variable speed drive, which changes the speed of the motor, and therefore the speed of the impeller. This controls the flow by varying the speed. Changing the speed of the motor shifts the pump characteristics, and therefore shifts the operating point of the pump and system. By enabling the pump to adjust to the system, significant energy efficiency improvements are gained. In fact, the Department of Energy estimates that variable speed drives save 3 to 6 terawatt hours annually. Now, while this classical model of pump and system characteristics are useful for understanding the fundamentals of pump operation, real systems that are changing dynamically are more complex and require continuous data collection and metrics to identify efficiency insights. This shows the distribution of efficiencies for different flow points as a pump is operated by a variable speed drive over a range of motor speeds, shown by the color bar. This efficiency and flow data is from 10 inflow pumps in a large New England wastewater treatment plant. This data is from August to December of 2019 and represents more than 8,000 data points. When we collect continuous data, we get these complex representations of real systems, operating dynamically over time. I want you to see that while the general shape of this best fit curve matches the classical efficiency curve, this real data is more complex. It's challenging to draw actionable insights from the data presented this way. We might ask questions like, what is the cause of the variation in efficiency? Or how can we improve our system? This highlights the need for efficiency metrics to aggregate the continuous data for comparison. One useful metric is true weighted efficiency, TWE. It's derived from the fundamental definition of efficiency as energy out divided by energy in, and substitutes in the relationship that energy is equal to power times time. This is a weighted average which weights the baseline efficiency by the energy at each operating point. Using the previous data, I built a Python tool to calculate true weighted efficiency for each of the 10 inflow pumps in the Northeast wastewater treatment plant. When comparing the pumps, we observed that 2 have higher efficiencies, several have a mid-range efficiency, and 3 have lower efficiency, with a total spread of 8% between the highest and lowest. This is surprising because all of these pumps represent the same installed hardware. Another way of visualizing this data is using a violin plot. This violin plot is just for pump 5, showing the kernel density estimate of the efficiency histogram. The width of the curve is a histogram of the number of operating points. And we see this top bulge, indicating that this pump operates fairly often at a high efficiency. We can compare this to pump 7, which also demonstrates a high average efficiency, but is operated much less often over the period of data collection. There are numerous other reasons besides efficiency why one pump would be operated more often than others, including maintenance and flow requirements. When we compare all the pumps, we see that pumps 5 and 2 are turned on the most, but that pumps 5 and 7 are the most efficient. Plotting the true weighted efficiency on the same plot, we see that this metric captures the same efficiency insights as the violin plots. One question we might ask is, if all pumps could operate as efficiently as pump 5, what would be the potential energy savings? Using the Python tool I built, we found that if all pumps could be operated like pump 5, the true weighted efficiency of the system would improve by 3%. This potential increase in efficiency could conservatively represent energy savings of 200,000 kilowatt hours and $20,000 annually. This is low-hanging fruit that can be identified using weighted average efficiency metrics. This example convinced me that accelerating the deployment of already proven technologies like continuous data collection and efficiency metrics shows potential for significant energy savings. Extrapolating from this specific example, if we could use current best practices, on this continuous data collection and efficiency metrics to identify system improvements, a hypothetical 3% savings across the US would save 6.7 terawatt hours annually. This is equivalent to 1.5 Hoover dams, and also equivalent to 11% of our currently installed solar capacity. And this would eliminate production of 3.4 million metric tons of CO2, equivalent to removing 730,000 cars off the road. This could save $700 billion in end customer energy costs. Furthermore, while data and metrics are useful for identifying operational improvements, these tools can also be applied beyond operation to both design and selection of pumps as well. Now, accelerating the implementation of these industrially proven strategies builds a foundation for developing optimization for system control. Traditionally, pump system optimization refers to intermittent assessment, data collection, and efficiency implementations. Energy audits help identify the greatest energy consumers at a facility, reveal opportunities for operational improvements, and detect issues with aging and underperforming equipment. And differing levels of audits are defined based on the depth of analysis and degree of detail, from a walkthrough to energy surveys and detailed analysis and modeling. Now, in conferences, white papers, company products, and newly implemented standards, industry is recognizing the importance of efficiency and scaling tools for intermittent efficiency optimization. Looking towards the future, we need to develop new tools for real-time optimization. Continuous data collection and feedback loops enable these optimization algorithms and feedback control. Integrating real-time sensing of flow, pressure, power, and speed for a pump and motor enables us to calculate efficiency. Developing databases, server resources, and analytical tools to manage the data are part of the technology implementation to actualize connected systems. Developing highly reliable systems is crucial to risk-averse utilities like clean and wastewater treatment plants. Data collection enables feedback loops between sensing, the optimization, and the controls for these integrated systems. These platforms need to be integrated for a single pump, but also for systems of pumps that might be operating in parallel. System controls, like turning pumps on and off or changing the speed of the motors, can be determined by maximizing efficiency and flow based on system requirements. This type of optimization is an important field of ongoing research. Steger and Pierce filed a patent in 2011 for controlling pumps based on measuring instantaneous power consumption and flow rate, and changing the speed of the pump in response to specific energy consumption. Zhang, Kusiak, Zhang, and Wei demonstrated the use of a neural network to predict energy consumption and flow rate, which was used in a bi-objective optimization model for a wastewater treatment plant. And on the right, Hilliard and Jamieson take a broader approach, applying Rasmussen's cognitive work analysis framework to identify energy efficiency opportunities. Translation of this research into industry is often slow, but can be accelerated by understanding stakeholders involved in operating and running these pumps. There is significant future work on the design and implementation of these optimization algorithms and developing the connected hardware platforms to implement connected systems. These systems can be applied across industrial applications for terawatt scale efficiency. All of this energy saved is energy gained. We need to accelerate deployment of continuous data collection, implement efficiency metrics, and also install efficient pump and motor hardware for the design, selection, and operation of centrifugal pump systems. These building blocks can then be integrated into optimized systems to enable dynamic pump control to adjust to real variable system demand. Scaled across industry, this two-part strategy of accelerated deployment and investment in new technologies demonstrates significant energy savings potential, with the ultimate goal of combating climate change by making a multitude of changes that sum to move the needle. If I haven't yet convinced you to be pumped about pumps, email me at hillaryj@mit.edu, and I'd love to continue the conversation. Thanks.